Thank you. First of all, thank you to the organizers for hosting this nice event and inviting me to speak here about a project that I've been working on together with my PhD advisor, Tristan McLaughlin, and a former postdoc at Trinity, Raul Pereira. And so I'm going to talk about the spectrum of n=4 Spiering-Mills theory, and in particular, statistical properties of anomalous dimension spectra. And I will study these in the planar limit, where we of course have integrability, but I'll also look at spectra at finite n. And there we lose integrability, but actually there is some structure there. We can describe the spectra or certain properties of the spectra by random matrix theory. And this talk is based on those two papers here from last year and ongoing work on those numerical spectra, and also on using on-shell techniques to extracting some of the spectra that we then analyzed. But yeah, let me start really at the beginning, or maybe first with an overview. I'll start with a quick motivation of what we can expect from such a statistical analysis of spectra. And then I'll move on to planar theory, so spin chain models that are interesting in the planar limit of supersymmetric conformal field theories. I'll talk a bit about data preparation and then about the level statistics analysis that we performed. And then I'll move on to non-planar spectra, and there I'll first discuss a few on-shell techniques that we used, and then also the level statistics analysis that we performed. Okay, but let me really start at the beginning. So we have n=4 Spiering-Mills theory, which is a quantum conformal field theory. So the spectrum I'll be talking about is this spectrum of scaling dimensions of local operators. And in n=4, there's a few closed sectors, and I'll talk about a few sectors during the talk, but let me just start with the simplest and probably best known, the scalar SU2 sector. So n=4 has gluons, fermions, and scalars. There's 6 real scalars, and the scalar SU2 sector is just spanned by 2 complex combinations of these, which I'll denote by X and Z. And then in the sector, we would be interested in local gauge invariant operators. And this is where I just take the X's and Z's and put them into traces. I can build single trace operators, or I can just multiply them and form double trace operators, multi-trace operators. And now associated to each of these operators I can build as a scaling dimension, and an efficient way to obtain scaling dimensions is via the dilatation operator. And we know the dilatation operator to one loop order for n=4 and also to higher orders in certain sectors. And in the SU2 sector, it has this well-known form. So just for my notation, so this is the tree level term. It contains the fields that span the SU2 sector, and there's also those functional derivatives X check and Z check that kind of annihilate X's and Z's. And so this combination here kind of counts the number of X's I have in an operator. This counts the number of Z's in an operator. And so in total, this first term gives me the length of an operator in the SU2 sector, which for a purely scalar operator, of course, is just the classical scaling dimension. And then at one loop order, this operator gets this correction here. And this gives then a correction, the one loop correction to the classical scaling dimensions, the one loop anomalous dimensions. And this operator now contains those products of functional derivatives. And this can really change the structure of the operator I act on. If I take this operator, act on a general single trace operator, for example, I can get back single traces, but maybe with different orderings of the X's and Z's inside the trace. But I can also get back double trace operators. And so this gives rise to a mixing problem. And then, of course, the question is, can we diagonalize this mixing? And for short operators, you can actually do it quite quickly by hand. But then as the operators get longer and longer, the dimension of this mixing matrix gets very big very quickly. And so this cries for a more general approach, maybe even an analytic approach to anomalous dimensions. And in the planar limit, this is achieved. The dilatation operator, the one loop dilatation operator, maps to the Heisenberg spin chain Hamiltonian. And so we can use integrability to solve the mixing and extract anomalous dimensions. And this, of course, extends beyond the SU2 sector to all of n=4 and also to higher loops. At finite n, we don't quite know how to do this diagonalization in the very general case. Again, you can, well, there are certain very impressive results for specific operators, but really in the general case, we don't know how to do this analytically. What we can, of course, also do at finite n, that actually reminds me. So we looked at n equals 4 for gauge group SUN, so n is the rank of the gauge group. And so, yeah, also at finite n, we can take this one loop dilatation operator and solve the mixing by hand for short operators, or if you want to be a bit more efficient, we can implement the dilatation operator into, for example, Mathematica, and then solve the mixing problem just by direct diagonalization. And then when you do this, then, well, you just kind of get huge lists of numbers corresponding to the one loop anomalous dimensions of the operators you're looking at. And then the question is, can we actually learn something from these numbers? Can they tell us something about the underlying theory that we can't really get a handle of analytically just yet? And so in order to approach an answer to this question, let me discuss it a bit more broadly. And for this, I have 3 spectra here. The first one on the left is just the spectrum of the harmonic oscillator. So here, all the energy levels are evenly distributed. Then on the other side, I have kind of the opposite spectrum. Here, I generated this spectrum by just generating random numbers in a certain interval. So in all of these examples, the mean level spacing is the same. But of course, if the levels are uncorrelated, they can be quite far, but they can also be arbitrarily close. And so this is the spectrum I'll call uncorrelated or Poisson spectrum. And an example for such a spectrum is actually the Heisenberg spin chain. And this is, of course, a very important ensemble for planar n equals 4. And so I'll come back to this during the talk. And then in the middle here, we have another spectrum that is kind of really in the middle. It is not quite so regular as this uniform spectrum, but also the levels don't want to get too far, they don't want to get too close. So yeah, and this spectrum is related to random matrix theory. So literally this spectrum I generated by diagonalizing a random matrix. And random matrix theory has different ensembles you can look at. And in this particular case, I'm looking at the Gaussian orthogonal ensemble. And this is the ensemble of all real symmetric random matrices. And this is actually a very important ensemble in physics. Already in the 50s, Wigner realized that the spectrum of heavy nuclei can be described or resembles the spectrum of matrices in this Gaussian orthogonal ensemble. And then this realization initiated the whole development of random matrix theory. And people realized that lots of physical models have spectra that can be described by random matrix theory, and in particular, this GOE ensemble. And then people realized that actually at a spectra of quantum models whose classical analogs are classically chaotic. And so there seems to be a universal feature of quantum chaotic models in their spectrum, in that it can be described by random matrix theory. And that then led to the conjecture by Boegas, Giannoni, and Schmidt that quantum chaotic models have spectra that can be described by random matrix theory. Yeah.
Just to make sure I'm understanding, if you, instead of plotting the levels, you were plotting the distance between the levels. So it's essentially a Fourier transform, I guess. Mm-hmm. You would see like a peak, a bunch of peaks, and then everything.
Actually, if you just give me a few minutes, I'll show you the plot for this. Yeah.
Okay, sorry.
Thank you.
Maybe a naive question, but what exactly is quantum chaos? I mean, is this a definition of quantum chaos, or is it?
Yeah, this is actually my next sentence.
Right.
Sorry. So yeah, so this, kind of this realization then led to the conjecture that quantum chaotic models have spectra that can be described by random matrix theory. And this was kind of motivated by the definition of quantum chaos of kind of the classical analogs of the theories. If they are classically chaotic, then the corresponding quantum model would be considered quantum chaotic. But of course, nowadays we're also interested in models that don't necessarily have such a semi-classical limit. And so this then lacking a good definition of quantum chaos, this statement was turned around. And so now it's often used in this direction where if you have a system and the spectrum can be described by random matrix theory, then this defines your quantum chaotic model. And this is also the direction in which I'll use this. And then similarly, people also realized that those uncorrelated spectra appear for integrable systems, like the Heisenberg spin chain, but many more systems. And this is like this famous conjecture by Berry and Talbot. And so really, there is something to learn from numerical spectra or from a statistical analysis. This analysis can tell us something about the nature of the underlying model, in particular, the existence and absence of integrability and chaos. And so this was kind of the rough idea for the project. We compute spectra in n=4, and then we look at the correlations in the spectra, and hopefully they will tell us something about the underlying model. And yeah, to kind of start off, so imagine we have implemented the dilatation operator in the SU2 sector into Mathematica, and now say we're interested in the spectrum of length 10 operators. So we would write down all length 10 operators, act with the dilatation operator, find the mixing matrix, diagonalize it. And then if you look at the eigenvalues, probably one of the first things you'd realize is that there are degeneracies. And degeneracies usually don't appear unless there's a reason, and a good reason for degeneracies are symmetries. And so looking at the dilatation operator in the SU2 sector, you can find some rather obvious symmetries. For example, there's a symmetry that exchanges x's and z's. And so if you have an eigenstate of the dilatation operator and just exchange x's and z's, then this will again be an eigenstate to the same eigenvalue. And this symmetry is part of a bigger SU2 symmetry, the residual SU2R symmetry, which arranges fields in terms of primary operators and descendants. And the descendants have the same anomalous dimension as the corresponding primary. And then there's more symmetries. For example, there's parity, which acts on traces by just reversing the ordering. So there's also degenerate parity pairs in the spectrum. And then in the planar limit, also the number of traces is conserved, and you can find degeneracies between single and double trace operators. And now actually, I don't want to go into too much detail about those symmetries. In some sense, they are known if you diagonalize the mixing and then look at the eigenstates of degenerate eigenvalues. It's usually not too hard to see what the symmetry is. So in some sense, we know about those symmetries. And if we left those degeneracies in the spectrum, they would overlay everything else, and we couldn't really look beyond. And in this context of a level statistics analysis, getting rid of symmetries and degeneracies is called desymmetrisation. And for this, you just look at sectors of fixed global quantum numbers. So for example, if you want to avoid those SU2 symmetries or degeneracies, you would only look at primary operators. If you want to avoid parity, then we would form states of definite parity and, for example, only look at positive parity states. And to avoid these degeneracies, we would only look at single trace operators. And now, so this desymmetrization is great to remove degeneracies and symmetries, things that we already know. But the problem here, though, is that in the end, we'll do a statistical analysis of the spectra. And this desymmetrization can quite drastically reduce the size of the spectrum. And so this will make the statistics poorer in the end. And for this reason, we did not only look at pure n=4, but also marginal deformations of n=4, where there's fewer symmetries, and so the sectors are generally bigger. And so it's long known that n=4 is part of this bigger class of supersymmetric conformal field theories. Leigh-Strassler classified these and found that this deformation of the n=4 superpotential gives, well, it reduces the supersymmetry down to n=1 supersymmetry, but the resulting theory is still conformal. This is an exact marginal deformation given one constraint on the new parameters lambda prime, q, and h. And then people went ahead, and in the planar limit, the Hamiltonian that you can find in the chiral sector spanned by the three scalars phi1, phi2, and phi3 is this object, which is a bit long, but it's again a nearest neighbor Hamiltonian. So the superscripts denote the site the operators act on. The subscript, they denote the flavor action. And so, for example, this contains E1,1, and this is just the operator that maps a phi1 to another phi1. And in this term, there's a E2,1, so this is the operator that maps a phi1 to a phi2. And yeah, so it has all those terms with the new parameters Q and H. And the authors of this paper, they also try to find integrable points. And they found these. One of them is the real beta deformation, where I turn off this H term here, and Q is just a phase. But there's more interesting points. For example, there's also one where this Q is set to 0, and I only have a H contribution. So now we can also take this Hamiltonian, implement it into Mathematica, and find spectra. And then what do we find? And maybe as a first thing to see kind of how sectors get bigger, I plot here the eigenvalues of operators in the SU2 sector of length 6 with 3 excitations in the beta-deformed theory. So these are the eigenvalues as a function of beta. At beta being 0, we are in the undeformed theory, and we can see there's degeneracies. And there's also quite a few protected operators. There's actually more protected operators that I don't plot. And then as we turn on beta, degeneracies get lifted, and also lots of protected operators become unprotected. There's still some level crossing. So at certain values of beta, there are still degeneracies, but well, they typically appear at values where beta over pi is rational, and that's where the beta-deformed theory corresponds to an orbifold of the undeformed theory. But at generic values of beta, the sectors would be bigger because there's fewer degeneracies. Degeneracies are lifted, and there are fewer protected operators. So now, yeah, again, we have implemented our Hamiltonian. We computed spectra. We're careful about desymmetrization. There's a few other things you have to do, for example, unfolding, which basically normalizes the spectrum. But I don't really have time to talk much about it. And so then once you have done all those steps, what can you do? What can you actually compute? And one thing you can compute is the nearest neighbor spacing distribution. So imagine this is these are my levels. And then for the nearest neighbor spacing distribution, I would compute the differences of nearest neighbor levels. And then what can we expect from such an analysis? Kind of coming back to the 3 spectra that I had at the beginning of the talk. For the uniform spectrum, so for the spectrum of the harmonic oscillator, there all the levels are just evenly distributed. So I would just always find one spacing, and in a normalized spectrum, it would just be 1. The mean level spacing is 1, and so we would just kind of find a Dirac delta function at 1. Then this blue curve here corresponds to the uncorrelated spectrum of the Poisson spectrum. So this is the Poisson distribution. And then the 3 other curves, they correspond to different ensembles in random matrix theory. I have here the Gaussian orthogonal, unitary, and symplectic ensemble. So the Gaussian orthogonal ensemble is what I discussed earlier. This is this ensemble where the random matrices are invariant under orthogonal transformation. So these are the real symmetric random matrices. And the corresponding nearest neighbor spacing distribution is this yellow curve that roughly goes like S times e to the minus s squared. Then for the Gaussian unitary ensemble, so the random matrices that are invariant under unitary transformations, so the complex Hermitian ones, I find the green curve. Yeah, I think there's a question.
So, just very rapid question. When you have something that just peaked, you just have one number. I mean, that is fixed just by one quantity, right? So on the other hand, modulo factors of pi and so on, all the other curves depend on two quantities. Essentially, one is the width of the curve and the other is where it's centered. So where do they come from?
For the peak?
For the matrix models.
Sorry,
you see what I'm trying to say. So you have the harmonic oscillator. Everything is peaked there, and that's okay because the harmonic oscillator has one parameter, which is just the 10, well, whatever you want to call it. Now, the Poisson distribution also has only one parameter, in fact. On the other hand, the other things are curves, which have a certain width and a center. There are two parameters there.
Well, yeah, that's I didn't really talk much about this, but I first normalized the spectrum, and so the mean level density will just be one, and so there isn't really another parameter in the spectrum.
I'm sorry, there's two of them. I mean, one, you can normalize one of them to one, that's okay, but you still have another one. That's what I'm saying. Your curves have one parameter more than the harmonic oscillator. That's all I'm trying to say. How thick is that curve?
I mean, yeah, for the Gaussian orthogonal. Oh yeah, the area. Yeah, it's the area. If you integrate over this this distribution, you just go one.
No, but it's still no. That's the same. There are still two parameters, and one tells me how thick is the curve. You can normalize everything however you please. That's okay. I'm just saying that there are two numbers. That's all I'm trying to say. A Gaussian distribution has two numbers. Right. No, but what I'm trying to say is that the difference between the peak and the others is literally the variance, given that there's the same average and there's the same area.
I mean, I guess like if you compute the eigenvalue distribution for a Gaussian orthogonal for a matrix in this ensemble, everything, it's fixed. It's just kind of this yellow curve.
No, okay. I'm sorry, I'm not making myself. Okay, maybe we discuss about that later.
Okay, so I talked about the Gaussian orthogonal ensemble, the unitary ensemble, and then there's also the symplectic ensemble. So these are the random matrices that are invariant under symplectic transformations. And so again, this Poisson distribution is conjectured to be related to integrable models, whereas the different random matrix theory curves correspond to different versions of quantum chaos. And so now, what do we find for the spectra of those Leigh-Strassler spin chains? And here I'm looking at a certain desymmetrized sector for length 11 operators. And this is one of those integral points where I set Q to 0 and H is just a phase. And here the red data points are our data points, and you can see that they follow the Poisson distribution. And you can also look at the spectra at different points in Q and H and find similar behavior. The data, this nearest neighbor spacing is described by the Poisson distribution. Then as you go away from those integrable points, you find that the spectrum is not described by this Poisson curve anymore, but is described by random matrix theory. And this now points really to the fact that the spin chain is non-integrable chaotic. And in this case of the Leigh-Strassler spin chain, we find that the random matrix theory ensemble that describes the spectrum is this Gaussian unitary ensemble. And so this is kind of the result for the Leigh-Strassler spin chain. We also looked at another spin chain in the SU2 sector. Because for n equals 4, we actually know the dilatation operator not only to one loop order, but also to higher loop orders. And so actually what happens if I take the Heisenberg spin chain and add a small 2-loop contribution? So the 2-loop contribution coming from the 2-loop piece in the dilatation operator in the planar limit. Now, of course, n equals 4, planar n equals 4 is integrable to all loop orders, but actually in this perturbative expansion in the coupling, if you kind of just chop off higher order terms, then we can't really expect integrability to hold. Integrability is there when I like really resum all contributions, but it's interesting to kind of look at it and see what comes out. And so this is the Hamiltonian to 2-loop orders. If this G is just lambda over 16 pi squared, if you set G to 0, you just get the Heisenberg Hamiltonian. If you turn on G, it becomes a next to nearest neighbor spin chain. And so for G being 0, of course, we expect integrability, and this is what we find. So the spectrum is well described by this Poisson distribution. Now, setting G to a finite value, small but finite value, we find that the spectrum is not Poissonian anymore, but can be described by random matrix theory. And in this case, it's this Gaussian orthogonal ensemble. So again, this doesn't say that planar n equals 4 is not integrable anymore, but if you truncate this perturbative expansion, what we find is chaos. And so now you might wonder, well, why do we find GUE in the previous case and it is GOE here? And this was already kind of realized very early on in the development of random matrix theory, that what specific ensemble appears in a given model is related to the discrete symmetries. And in particular, you can show that for Gaussian orthogonal ensembles, these are related to models that are time reversal symmetric and have a rotational invariance. And basically you can just take those two symmetries, and in a suitable basis, the Hamiltonian would be real and symmetric, and so is a member of the Gaussian orthogonal ensemble. And more generally, if you can construct a time reversal operator from a complex conjugation and a unitary operator K satisfying this condition here, then you can do a similar procedure, and in a suitable basis, the Hamiltonian will be real and symmetric. And in the SU2 cases that we looked at, so for example, for this spin chain, you can actually construct such a time reversal operator out of the complex conjugation and the parity operator. For the Leigh-Strassler spin chain in the SU3 sector, this construction breaks down, and we can't, we didn't find a time reversal operator. And indeed, this kind of, if you have no time reversal invariance, this is related to Gaussian unitary ensembles, and this is exactly what we find. Okay, so now this concludes this level statistics analysis for the planar theories. Now I want to come to non-planar spectra. And first, I want to take a few minutes to discuss an on-shell approach that we use to obtain some of the spectra. Of course, we know the dilatation, the one-loop dilatation operator in n equals 4 also at finite n, so we can do a statistical analysis there. But again, for better statistics, and also because contains rich physics, we can look at deformed versions. And so for this, so we extracted the dilatation operator and the beta-deformed theory at one loop order in the scalar sector from this on-shell method that is based on this kind of curious relationship between the dilatation operator and the scattering matrix. And at one loop order, it's given by this expression derived in this paper here. And so here on the left-hand side, I have the one loop dilatation operator, and in particular, the component that maps an operator OA to another operator OB, so A and OB. And this object here is the overlap of an n-particle on-shell state with the off-shell state created by a local operator OB acting on the vacuum. And so pictorially, it looks like this. Actually, there is an off-shell momentum in here that I leave implicit, but it amounts to just an overall delta function. And so this object is a form factor. And in this equation, I evaluated a tree level, and for a tree level, form factor to be non-vanishing, the field content in the external state has to be in one-to-one correspondence to the field content in the operator. And so this then would be a minimal form factor. So this is the left-hand side. On the right-hand side, I have two terms. Again, I have a minimal form factor of the operator OA now, and this multiplies an infrared divergent factor that cancels infrared divergences in this term here. And it's related to when particles in the external state become soft or collinear. And so this really is the main piece of this equation. This is a convolution of the scattering matrix and a form factor of the operator OA. And pictorially, it looks like this. So I have a form factor of the operator OA, and two of its external states, they scatter with the scattering matrix of the theory. And here, those red lines denote that I put the intermediate states on shell, and then I integrate over the on shell momenta and sum over all possible intermediate states. And so this relation kind of says that the action of the one loop dilatation operator can be obtained from the one loop unitarity cut of a form factor. And so by kind of realizing what external states I can put here in the equation without this term to be vanishing, this kind of tells me what operators a certain operator can mix into. And to be a bit more explicit, let's assume that this just contains scalars. And in particular, I want to have an x and a z here. Then, well, in the undeformed theory, you might actually be worried. This amplitude is then just the 4-point, a component of the 4-point superpactalar amplitude. And actually, it has a component where those two particles here are fermions. And if this was really non-vanishing, then this would imply mixing out of the scalar sector. And actually, if you do the computation, put in the parametrizations here and integrate over the on-shell momenta, then you find that this contribution vanishes. So the scalar sector is still closed, and the only non-vanishing contribution comes when I have two scalars here on this side too. And now really you have to kind of sit down, plug in the amplitude in, for the undeformed theory, you can just extract it from the Pach-Taylor expression. This is the color addressed amplitude. And so then you plug it in. And I don't want to really go into details, but basically from the T-channel term, you find an infrared divergence that cancels this term. And from the S-channel term, you find something finite that then gives you the dilatation operator in the SU2 sector. And so then now that it works for the undeformed theory, we can go to the deformed theory. There we know the beta-deformed amplitudes too. And this amplitude now has 3 terms. This term here gets just inherited from the undeformed theory. So this is exactly this term here. And this again just gives rise to an infrared divergence that cancels this infrared divergence. And then there's also this single trace term that is kind of the deformed version of this. I can't write it in terms of those undeformed structure constants anymore, but I can write it in terms of deformed commutators. So the deformed commutators contain just the usual 2 terms of the commutator, only with phases depending on the flavor of the external particles. And then there's a generally like new term, a double trace contribution in this beta-deformed theory. And then if you kind of sit down and do all the calculations, what you find is that the beta-deformed dilatation operator looks like this. So it has a single trace contribution, only like that kind of gets inherited from the undeformed theory, only that the commutators are deformed now. And then there's a new term, a double trace contribution. And in the limit where beta goes to 0, this is just the undeformed dilatation operator again. And so this is the result in the SU2 sector. You can also generalize it to the full scalar theory, and this is what we find. So those 2 terms are kind of the generalized terms in the SU2 sector, and these are new in the SO6 sector, and they contribute when you act on a singlet state. Okay, so now that we have the dilatation operator, we can again look at spectra, and also here in the deformed theory, we will have bigger sectors. This is the plot that I already had in the discussion of the planar theory. So here we saw when I turn on beta that degeneracies get lifted and protected operators become unprotected. Now in the finite n theory, already in the undeformed theory, certain degeneracies are lifted, but again here, if you turn on beta, a lot of states become unprotected. And so in general, you'll have bigger sectors. And another feature of the spectrum is that the levels, unlike here, they were crossing, here they seem to repel each other. And this is already a sign of quantum chaos. And to be a bit more quantitative, we again did a nearest neighbor spacing analysis. Here for the beta-deformed theory, this is again in the planar limit, where the spectrum is well described by the Poisson distribution. And then at finite n, we find this. And so here the spectrum is described by random matrix theory, so pointing towards the chaos of the theory. And in particular, it is well described by this Gaussian orthogonal ensemble. And we can perform a similar analysis in the undeformed theory. At finite n in the SU2 sector, we find this. So here the statistics is not quite so good, but still you can see that the spectrum is well described by this Gaussian orthogonal ensemble. And then we didn't only look at SU2, but we also looked at the SL2 sector, so the sector spanned by one scalar and one covariant derivative. And similarly, we find that the spectrum can be described by this Gaussian orthogonal ensemble. And so from the statistical analysis of the spectrum, we can actually really see the integrability. The integrability is manifested in the spectrum. And at finite n, we lose integrability, but still there is some structure. And we can describe the spectrum by random matrix theory, in particular this Gaussian orthogonal ensemble. And so these are the results from a statistical analysis of the spectrum. But actually, when you solve the mixing problem, you get the eigenvalues, but you can also get the eigenstates. Can we also learn something from the eigenstates? And one thing you can compute is the information entropy. And for this, you first have to pick a reference basis. We just used kind of the standard basis of multi-trace operators. And then I decompose a given eigenstate in the spaces, extract the coefficients, and plug it into the information entropy. And then what can we expect from such a quantity? I'll probably be a bit quicker here, but if you have an eigenstate that is evenly spread over the whole basis, so those C's are just constants, then what you find is that the information entropy is just the log of the size of the spectrum. If the state is exponentially localized over a certain number of states in the spectrum or in the basis, then what you find is that the information entropy is the log of the E times the size of, or the number of states it is localized over. And so the information entropy gives you kind of a measure over how many states the state is localized, over how many basis states the eigenstate is localized. And random matrix theory also makes predictions for this information entropy. And for the Gaussian orthogonal ensemble, what you find is this quantity here. And this term here is roughly 0.48. And so we can take our eigenstates from the mixing problem and then compute the information entropy for each of those eigenstates. And what we find is this plot. So here is the information entropy normalized to the GOE prediction. And we compute it for each of the eigenvalues. I have one information entropy. And we compute it for, in the planar case, the yellow points, and the finite n eigenstates, the blue dots. And you can see that for the finite eigenstates, the information entropy is close to the GOE prediction, whereas for the planar eigenstates, their information entropy is generally lower. And so again, we see that at finite n, not only the spectrum, but also the eigenstates are well described by random matrix theory. Okay, now I just quickly want to wrap up. So I started with this analysis of spin chains that are interesting in the planar limit of n equals 4, but also marginal deformations of n equals 4. And we could see that using such a level statistics analysis, we can learn something about the theory. We can see integrability at integrable points, for example, of the Leigh-Strassler spin chain. And then as we go to non-integrable points, we could see that the spectrum is described by random matrix theory. And then at finite n, we find that there is no integrability anymore, but the spectrum can be described again by random matrix theory, in particular this Gaussian orthogonal ensemble. And not only can the spectrum be described by random matrix theory, but also the eigenstates. And so this then lets us to the conjecture that n equals 4 Spiering-Mills theory and its beta-deformed version are chaotic at finite n and described by this Gaussian orthogonal ensemble. And I haven't talked about this here, but we find similar behavior at small n, so where the rank of the gauge group is smaller than the length of the operator. And there's like more relations between operators, and so sectors are a bit smaller. And then maybe more generally, I think the statistical analysis of numerical spectra just from direct diagonalization can give a good insight into the underlying theory, in particular when we don't really have an analytic approach yet. And so since it's quite a general technique, you could extend it well to other sectors of n equals 4, maybe other gauge groups, and then of course also to other theories like ABJ. And then also going forward, maybe we in our analysis looked at the nearest neighbor spacing distribution, and this can really tell us it's Poisson or it's random matrix theory, what ensemble. In the paper, we also looked at a long range observable, the spectral rigidity, and that also can tell you, is it Poisson or is it a random matrix theory? But it also tells you a bit about the range over this is true in the spectrum. So there's a bit more information there, but I think going forward it would be interesting to look at more fine-grained observables. So for example, for us, the chaos that we find in the spin chain models and the chaos from finite n spectra looks kind of the same. And I think it would be interesting to see whether there's actually differences in their chaotic features. And then also maybe if you want to look at things like thermalization, so you would want to compute expectation values of some time-dependent operators. We kind of always looked at the standard multi-trace basis, but at finite n, maybe the basis of the Schur polynomials would be more natural. So that's the basis where the two-point correlation function is diagonal, or for the SU2 sector, the restricted Schur polynomials. And then, this project was kind of inspired by the realization that for late time fluctuations of large ADS black holes in the SYK model, they can be described by random matrix theory. And then, of course, if we could somehow connect with statistical properties of the dual gravity theory, that would be great. And then finally, that we find this random matrix theory description in the finite n spectra is actually quite cool, and that also spectra of more complicated theories like QCD can be described by random matrix theory. So despite all the symmetry, all the supersymmetry, the conformal symmetry, we still find the spectrum that is incredibly generic. And so maybe the hope is that although this theory is so special, maybe we can actually connect with more physical theories. But then, of course, we cannot actually solve those theories. They are non-integrable, they're chaotic. So maybe this is a hint for us that we cannot actually solve non-planar n equals 4. But then, of course, unlike the other theories, we have this integrable limit. And so the hope is that we can use this integrability to solve the non-planar spectrum. And just as a first step, Tristan, Raoul, and I, we looked at the non-planar spectrum as a perturbation around the planar solvable theory. There, in this approach, the planar integrability really organizes you the non-planar corrections, and we found quite compact expressions at one loop order. But yeah, I think I'll finish with this, and thank you.
Thank you for the very nice talk. Are there questions?
Thank you for a nice talk. Maybe about the last point. So in general, you have now a double expansion in the 't Hooft coupling and in 1/n. And I guess already several years ago, there were works by, for instance, I think Beisert, Christiansen and Staudacher, and others certainly, where they were seeing that this double expansion can give you problems in general. I mean, that it really matters whether you do things in one order or the other. You can get singularities. So in light of that, maybe you can explain it a little bit more. What do you mean when you say that you can get, or that you might hope to get analytic non-planar spectrum from the planar integrability?
I mean, you have to be really careful about the order of limits, and we kind of only computed the one loop order corrections. And then, so we first do kind of perturbative expansion in the coupling, and then do the perturbative expansion in 1/n. And I mean, yeah, you have to be careful. Sometimes there's kind of a lifting of the non-planar corrections due to degeneracies, and then you have to really resum the contribution of the expansion. But for kind of the cases where you can really do where this is well defined, I think you can compute things. And I mean, there are some issues with degeneracies in the spectrum where you can't actually do the non-degenerate perturbation theory. And that's why actually that was also one of the reasons why we looked at the beta-deformed theory. There certain degeneracies are lifted, and then we can compute the non-planar corrections in this deformed theory. Mm-hmm.
What about finite coupling? I think we have a good control about the spectrum at any coupling. Could you make an analysis of this level spacing for finite coupling?
If you give me a spectrum, I can do that.
Well, you can use the quantum spectral curve or TBA.
Yeah, we haven't looked at, sorry? This would be planar, yeah. And I mean, you could, again, I guess from the spectrum confirm the integrability, but yeah, I mean, we kind of also, I talked about the two-loop contribution in the spin chain, but you can also imagine adding a little two-loop contribution at finite n, and this does not change the general behavior. It's still GOE, although strictly speaking, actually, like in the perturbative expansion, of course, I can't add like a small contribution, like for a finite G. But yeah, in principle, we could extend it also to higher. Mm-hmm.
Thank you.
Alessandro's question essentially one more time. So since, as you know, I entertain an interest in this because of the non-planar possibilities it might open. So let me ask precisely, the first example of this degeneracy that Matthias and the others noted in the old days is essentially, I think, when you have a length 6 SU2 sector BMN problem, then you can mix into, there's an eigenstate that has the same anomalous dimension as Konishi. And you can therefore add in a length 2 vacuum times the length 4 Konishi descendant. So I was wondering, that's not the parity, the degeneracy, it's just the fact that the product of the two anomalous dimensions in the double trace operator will give you the same as before. Do you see this example in your plots? I mean, shouldn't it be in these wavy lines that you had? I mean, can we sort of see whether that gets lifted or not? That, exactly, yeah.
So this here is actually degeneracy between a single trace operator and a double trace operator, and that gets lifted in the beta-deformed theory. Yeah.
Oh, brilliant. So then we can continue what I have been trying to. Okay, thanks.
Okay, so my question is precisely about this plot. So when I saw this plot, it reminded me a little bit of a work some years ago by Grisha Korczemski when he was discussing level crossing. In that case, the marginal parameter was precisely the gauge coupling, I think. So it was saying like we see the crossing in the planar spectrum, but we shouldn't expect the crossing to happen at finite n because there are some no-go theorem, so that you cannot have level crossing at finite n. And so it was precisely showing that when you get close to the crossing point, I think you have some universal behavior. But in that case, as I said, the marginal parameter was the gauge coupling. So is that you're telling me that this is already a sign of chaos? Should I expect chaos also if I look at finite coupling in a sense?
Yeah,
finite Toft coupling.
Yeah, exactly. In his work, he really looked at the coupling as a parameter. Those plots are really just for one loop order. So there's no, the coupling isn't a parameter. And here we use the beta deformation as the parameter. But if you, yeah, and this theorem is, I think, by von Neumann and Wigner, and they kind of made the conjecture, they proved that if you have a general spectrum that depends on two parameters, then if you have a general spectrum that depends on a number of parameters, you have to at least tune two to land on a degeneracy. And this is what he showed here. But here we are kind of just we just have one parameter, and here it's kind of, this conjecture doesn't hold because there's additional symmetries, and that's why we see those level crossings. And this is kind of if there are symmetries, then you can have exceptions to this.
Yeah, this I understand. What I was wondering is, since but then the same phenomenon happens for the coupling. I mean, if I think of the coupling as a marginal parameter, could I expect, I know this is a one loop analysis, but in that case, the claim was level crossing should not have, this repulsion should happen also at finite coupling, finite Toft coupling.
If you have another parameter, like the beta parameter, then you have two parameters, and then, yeah, there could be accidental degeneracies if you fine tune both of them. But yeah, we didn't look at it because we just looked at the one loop case, yeah.
I have a question. Have you looked into how the peak of the distribution changes in N? Like after the breaking of integrability?
We try to look at this a bit. It's a bit hard for just from kind of numerics. If we had analytical control, that would be better. But actually, I think in my backup slides, I have a plot that we made quite early on. And here you can actually see that you don't have to go to too high values of the rank of the gauge group to already see this Poisson behavior. And this intermediate regime, you really see like a superposition of this Poisson behavior and the random matrix theory behavior. But yeah, just from the numerics, it's really hard to make a conjecture on the exact distribution that interpolates the two.
That's okay. I must ask him because there was a paper by Poshgai and Takahashi in XXZ perturbation and breaking integrability, in the terms that I think the peak position and how what power law it goes to the Poisson distribution. The exponent can tell you if it's like a weak breaking of integrability or strong breaking, and like different levels of quantum chaos happening.
I mean, there are certain interpolating functions, and you can plot it to maybe.
I mean that if you're just taking the peak position of the distribution and taking that value and just seeing how it approaches zero or what power law behavior it has, and that tells you something about what kind of integrability breaking you have and what kind of quantum chaos.
Yeah, that sounds like it would be interesting to look at, but we haven't really looked at this transition much.